This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
That's not good. Right. Worked. Okay, well, excited you guys made it to the second lecture. We're off to a great start. Should get this up on the screen and get cracking. So we do have quite a bit of ground to get through. Good. So we're still in the fundamentals module. Yesterday was the hand waving welcome to thermodynamics. It's an interesting thing and you should study it, aside from the fact that you have to. Today we're going to get quickly into the ground of defining our world. To use the tools that we've got in this subject, we need to set up a whole bunch of definitions. So one of the things we need to do is work out how will we decide what we're working on, how do we work out the properties of what we're working on, and how do we even describe the processes that are going on. So that's today. The stuff that we define today, we will use over and over and over again every lecture. And so we're going to play around with it at a conceptual level today, and then by, in a week's time, you'll forget that it was ever defined. It'll just be the way that the things are in thermo. But it's worth us going through step by step, because we use the ideas of a system and its boundaries to define the problem that we're solving. I said yesterday one of the big breakthroughs that Sadi Carnot made, one of the big innovations he made, was to define that the thermodynamic processes were taking place through the mechanism of a working fluid or a working substance. To understand what happened to that substance, you need to know its properties, which is to say things like temperature, pressure, volume, this kind of stuff, and how they change when we do a process to them. So the whole point of this is to work out what happened or what will happen after a change. So we need to know to what, and to what values of what, and then because of what. So, system boundaries, properties, and processes and equations of state. The equations of state are how do these things all connect. So that's today. What's system? What's system boundary? Why on earth would we use one? If I tell you that something's changed in this room, and you decide to analyze it by looking at the global average temperature, you may have defined your system boundary in a perfectly valid way for you, but an unhelpful way for solving the problem. If I want to know whether the temperature here changed by 1 degree or 2 degrees because of how many people are in the room, you probably should have said, I'm just going to think about the room for now and forget about the outside world. That exercise of drawing a line around your problem and saying what I'm not going to care about and what I am going to care about is one of the choices you make as an engineer, is one of the choices you make as a thermodynamic engineer. When you get to doing an analysis on your own, and you're not having a handheld in the learning of the tools, that's one of the first things you do. And after a while, these choices may seem almost trivial. So, well, of course, if I'm analysing the room, my boundary is the room. Of course, if I'm analysing The computer, my boundary is the computer. But it's an exercise that needs to be learned, and it's a definition philosophy that needs to be learned, so that when you do it, you realise you're making a choice that either makes your analysis hard or easy. How you set your system boundary affects what maths you will use, it affects what terms you can cross off from equations, and it affects what tools you can pull in to do that analysis. So even though it almost feels trivial, by the end, particularly you get to exam time, you're like, oh, just I want to get the formula on, put the numbers in the formula, get an answer. Forgetting that you have already, almost by instinct, chosen a system boundary. So we're going to look at what you can do in choosing those boundaries. The system is the matter or the region that you're studying. The surroundings is everything else. It's basically the universe, unless your system is the universe, in which case there isn't an everything else. The boundary doesn't need to be a physical boundary. It can be a real or an imaginary line between the system and the surroundings. Sometimes they're quite obvious physical boundaries. If I have a piston cylinder, the walls of that piston, so a piston cylinder like inside a car, the piston and the cylinder that it's inside and the cap of that would make sensible boundaries. And they are physical walls that have a definition. If I were analysing the flow through this room, the airflow through this room, and trying to understand what temperature of the air inside the room is my system. These walls make a good boundary, but at the doors I've got something funny, because one of the doors is open, so the space of the door is not a physical boundary, but it's probably where I'd stopped calculating. And so it's an imaginary boundary, but it's still part of my system boundary. So these are the choices you make. Early on, we'll say, I'm going to define this for you, but you need to be realising when it's your independent analysis, you get to choose where the maths begins and where it ends. The nice thing about drawing a system boundary is that everything outside of the boundary you get to almost ignore. Now that gets interesting sometimes because you look at a complex system and the idea of ignoring the complexity that's outside of your actual calculation seems weird. If I was looking at a car engine, and I was just analysing inside one piston cylinder, forgetting about all the rotational mechanics of the crank, forgetting about the exhaust, forgetting about the fuel tank sloshing around with fuel, forgetting about the process of combustion altogether and just thinking somehow magically I get heat, these exercises can feel artificial, but they save you a lot of time in the analysis. Sometimes your system might be two molecules, and you're just analysing how they bounce, and then you are forgetting about all the other molecules and what have you. So you have choices that you can make. Early on in the subject, we have some really standard systems that we use for analysis because they have nice properties. So you will find us looking over and over and over and over again at a piston cylinder. And sometimes the piston will be at the bottom and sometimes the piston will be at the top. But it'll generally be a container, and often we'll imagine them as spherical cross-section with a disc that's either sitting, floating on a liquid or a gas, or a disc that's being pushed by something, like in a car. That system has some really nice properties. It's got some fixed boundaries, it's got some moving boundaries. Now there's some new terms. All the way through the first half of this, in fact, all the way through the next 6 weeks, we will keep learning new code words. They're words that you've encountered before. You may recognise the word, you may understand the word, but they have a special use in thermodynamics. If I tell you that I have a fixed boundary, it has a mathematical implication to how you're going to solve the problem. If I tell you I have a boundary that can move, it has a mathematical implication on how you solve the problem. So often I'll be highlighting words or bolding words, and I'll try to draw your attention to them. When they are not just an adjective, they're not just a description, they are triggers or code words for how is my maths going to be applied. So in the system, fixed boundaries are pretty easy to imagine because they look like walls, even though they might be imaginary boundaries. The fixed boundary of the door that's open at the back of the lecture theatre is not moving, but it doesn't exist. The moving boundary, any surface that is changing. So a balloon has a closed surface, a closed boundary, but that boundary, as I'm analysing its change, as I'm analysing inflating it or deflating it, that system boundary is changing, it's moving. So the entire system might have one open spot where I'm putting the air in, the pressure will be changing, the temperature will be changing, the walls and the volume will be changing, and I have quite a complex system, but I don't care about the outside world. I've defined my boundary as the surface of the balloon. The piston cylinder is very useful this way up. If I have an amount of gas inside a piston, it has its own pressure. Okay? So if I sit a disc on top of it, a disc of metal, that disc will sit somewhere. It won't go all the way to the bottom of the chamber because it can't, because the gas can't compress infinitely. So it will sit somewhere, and it will sit somewhere nicely, exactly at the balance of the forces. The disc has a weight, so it's exerting a force down. The pressure's trying to stop that. It has a force exerting up, pressure times the area. We'll do that a bunch of times over and over again. So the steady state equilibrium of this guy has this really nice combination that if I know the mass of the disc, I also know the pressure in the chamber. And at the early stages, we always throw away friction. We're not interested in whether this disc is rubbing on the wall, so with Teflon walls and what have you. But that thing gives us a really nice tool for analysing how does the gas change as I change its pressure, temperature, volume, what have you. Closed and open boundaries, again, code words. What I'm interested by when I define a system boundary is I don't care what is the surroundings, but I do care the influence that they can have on my system. There's two major ways you can influence your system from the surroundings. One is by mass coming into the surroundings, coming into the system, and the other is by heat transfer in or out of the system. The mass transfer can only happen if I have an open boundary. So the reason why we have this code word of closed boundary, if I tell you closed boundary, I'm also telling you there can be no mass transfer from the outside world to the in or from the inside world to the out. The mass of my system is fixed if I use the code word of closed boundary. If I use the code word of open boundary, my mass can change and I will probably need to keep track of the mass of my system. And I'll need to keep track of the mass flows across the boundary. Both a closed and an open boundary can have heat transfer across them, unless I deliberately tell you a code word of an insulated device, in which case insulated will mean no heat transfer. So the difference between a closed system and an open system: the closed system has a fixed mass and can't change its mass. The open system, the mass can change. Both of them, heat can transfer across the boundaries. So I've drawn now up on the top right another system boundary. It looks a lot like a trapezium. It doesn't look anything like any piece of mechanical equipment that you've ever seen. So we also have code pictures for system boundaries. And as we progress through different pieces of equipment, you will learn, or I will teach you or show you representative pictures for each piece of equipment. I do have a pen. I might actually just quickly jump across to the doc cam to show you what I'm talking about. The one that was up there, on the right, and I labelled it a nozzle. A nozzle isn't doing anything particularly magic. It starts from something big, funnels things down to something small, and on the way, everything gets a bit faster. If I've got a mass transfer going through that thing, if I squeeze it down, it's going to get faster out the end. It's the point of a hose. Large, big pipe coming from into my house, but at the end of the hose, tiny little constriction, the water accelerates, and I get a great big spray across the garden. That's a nozzle. We have the reverse thing also possible, but I try to simplify that as much as I can. I don't care what the shape of the hose is. I just go something that goes from a big area to a small area, assuming generally I go that way. I've drawn walls here. I need to define my system boundary, and so a sensible choice for me to simplify my maths is to say that's a straight line, pretend it's a straight line. I will draw some imaginary boundaries at the inlet and the exit of this nozzle. And the only thing I've learned over the years, the only thing I really care about is what mass came in, what mass went out, its properties, we'll cover those in a few slides' time. So that I can work out how fast it's moving, I'll probably also need to know the area of these guys, so that I can understand how much I've squeezed it down as it's flowing through, and I probably need to know the initial velocity. So there's just the exercise of saying how fast is the water coming out of a nozzle suddenly requires me to know what's my system, where are my boundaries, what's crossing which boundaries. These guys are walls, so no mass is going out the walls of the nozzle, but mass is coming in the inlet and going out the outlet. So that's the systematic structure for setting up our problem. That shape is a nozzle. There are other shapes. I will do them over and over again. The main stuff we play with are piston cylinders, turbines, compressors, nozzles, and throttles. Nozzles and diffusers. And so the opposite of that, this is a nozzle, this is a diffuser. A diffuser does exactly the opposite thing of a nozzle. Takes a fast flow and lets it slow down. If I drew them like this, these are my code pictures for a compressor and a turbine. And I still need an inlet and an outlet of both of these guys. So I draw little dotted lines. The compressor's job is to compress things. So again, going from this way to this way, it gets from bigger to smaller. The turbine's job is to do the opposite of compressor. It lets things go from little to big. And then if I was drawing a piston cylinder, I would probably draw a box. So I can draw system boundaries quite simply. I can sketch them quite quickly in an exam or an assignment. I can draw them with dotted lines to symbolize an imaginary boundary, or solid lines to symbolize a wall. And there's another code that you can use for I'm not going to allow heat transfer, and that's to do little dashed lines like this. And that's pretending I've got some kind of insulation around the thing, which isn't going to allow any heat to transfer. So that's some of the pictures we use. If there's any new picture, I'll show you on the way, saying this is our secret diagram for a throttle or whatever. Let's get back up to the computer screen and the slides. Okay, good. And then having done that, having set the rules for we're in charge of how we set our system boundaries, I've got, rather than sort of slowly jump from one picture to the next, I've got a picture of a car engine, a jet engine, and a Cut 11s. And we're going to have a look at where are my system boundaries. So, zoom in even more. How far can I zoom? If you haven't seen inside a car engine, it's probably about time you did. This is a 1, 2, 3, 4 cylinder car engine. So now we know where the cylinders are. Here, 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 and here. Well, the pistons are here. Cylinders are what the pistons are sliding up and down in. And there's all sorts of machinery around it to make all this work. So it's crankshaft to push everything up and down. There's valves to let the fuel in and out. There's a timing belt to make sure all the things are moving at the same time and in a way that I want them to. And eventually there's a shaft that connects it out to the gearbox and then to the wheels. So, where's my system boundary? The engine. Which bit's the engine?
Depends on what you are testing.
That's a different answer. That's a different answer to the engine. Why is it different?
Because if you are testing the cylinder, you put the boundary around the cylinder.
So the engine could be this. The cylinder could be this. Are there any other system boundaries I can draw? No other system boundaries I could draw.
I don't know much about engines.
Doesn't matter. Are there any other? Can you see anything there that it would be possible to analyse?
Maybe like exhaust pipe.
So let's imagine, maybe it's cut off from here, but let's imagine the exhaust goes that way. I could draw an exhaust pipe. Sorry? The valves? Yep. So I could draw here, let's say. There you go, right up the back, Levi.
The area.
Sorry.
The fuel tanks.
Yep, so we've got an air cleaner in here, the fuel tank, carburetor. So the carburetor is where the fuel and air gets mixed in, so somewhere over here there's probably a fuel tank. Okay, so we could analyse that. Which one of these is the right system boundary? Yeah, you had the answer already, so it's kind of deliberately coming back to it. You cannot say. Why?
Depends on the problem. So definitely.
It's not defined, it depends on the problem. What's the problem? There we go. That's it. I'm not deliberately trying to trick you or anything, and just trying to hammer back down to this point of I can't tell you what the system boundary is until you tell me what it is you're analysing. Even after you've told me what you're analysing, I can't tell you what the system boundary is because it's your choice as the engineer to make your life the simplest it can be while still being useful. So the simplest boundary to analyse anything about this could be the universe over infinity time, in which case I know the analysis of this, it ends up being a uniform temperature with everything else in the universe of approximately 0 degrees Kelvin, maybe just a little bit above, with atoms distributed as energy everywhere. A valid system boundary, but not a useful one. So you're choosing the system boundaries and the time boundaries that allow you to solve your problem in the simplest and most precise way. Now we talk about the time boundaries as well because the process of a cylinder moving from here to here can be analysed completely. The process of the cylinder doing a full cycle can be analysed completely. The engine driving from here to Sydney can be analysed completely, including putting fuel into the fuel tank a couple of times, depending on your car. You could analyse the car and the engine so that you've got some idea of road resistance on the tyre and wind resistance on the car. It depends on what you're trying to solve for. If you're trying to solve for the efficiency, the drive cycle efficiency of long-term driving, you'd probably need to understand the car and its performance on the road with wind. So my system boundary is now the whole car. If I'm interested in understanding how much heat was released during one combustion event, then I just want to do the bit where I'm almost at the top and all my fuel burns and I just come a little bit back down again. In the gasoline engine, boom, burnt. The impact of that, now I've got heat in the chamber, might be a change in pressure and a change in the movement of the cylinder. I have a different system over a different time, the same system over a different time. I have choices to make. If I did it on a gas turbine, so the piston cylinder there had a lot of closed boundaries, it had some open boundaries as well. If I did it on the gas turbine, same exercise, I could be analysing the plane, I could be analysing the energy system of the manufacturer of planes globally. I could be analysing the gap between one turbine blade and the next and watching the airflow just over that space. I could be analysing, well, that's not a turbine blade, the fan at the front. I could be analysing just one turbine disc here, and pretending I didn't even care what was happening with each blade. I just want to know how much air went in one side and came out the other, or the entire turbine. One of the other neat things that happens with the system boundary in thermo, if I drew the system boundary for a turbine, air needs to come in somewhere, air needs to come out somewhere. If it's a steady state, the mass that comes in has to be the same as the mass that comes out because it's not changing with time. So
Sorry, I can't see.
you're right. Thank you. That's the kind of feedback I need. So I've got a mass dot in and a mass dot out of a turbine, and that's just a picture of this guy. And I need a shaft that comes out of it so that the point of the turbine can be reflected as work done. I've sketched out that turbine. What can't you see in that system? Can't see a single turbine blade or a disc or anything, any of the machinery that's inside the turbine. So not only by defining the system boundary, not only have I thrown away all of the outside world, I've also thrown away all of the inside world. So really what I'm interested in is what is the change of my system and its properties. So if I define the system as one turbine blade, that's what I'm thinking about. I'm thinking about the change in the temperature, the density of the steel or titanium. Has it grown longer, shorter, whatever? The space between two turbine blades, I'm interested in how much air was flowing through them, what change in pressure, what change in temperature, what energy was I able to release from it so that I could use it as work. If I'm interested as the turbine as a machine, I'm not analysing in between each blade. And so inside here gets to be ignored. And that's another thing, a really nice simplicity that comes with some of the macro thermodynamic analyses. Likewise, if we look at a human being, I could analyse a leg or a body. I could analyse that over a sprint or a lifetime. I could analyse the head, but ignore the brain, just understanding what went in and what went out. But also maybe what went in and what went out. Just one hand, one arm doing work. Where's the energy coming from the arm? Do I need to understand, am I using up just the arm's worth of energy, or do I need to connect it to the body system so that I know where the energy flow was? If I'm doing it over a length of time, do I need to understand the energy in and the energy out of the body? And that depends on what kind of human system you're analysing. As an athlete, you're interested in each aspect of those because you want to understand, without putting any extra energy in, how much power can I get out of my body? As well as long-term over my lifetime, long-term over the season, long-term over the week, over the day, over the game, how much energy can I get out? So what do I need to put back in to keep the system functioning? How do I keep up maximum efficiency, etc., etc., etc.? All of those require different settings of system boundaries. Let's get back onto the computer. Any questions about system boundaries before we jump on? Okay. So that was all about the simplifications we make in our world and the choices we have to make right at the very beginning of the problem. On the way of starting to wave my hand and describe these things, I've already jumped into two other ideas. One is that one of the main things we'll be doing is looking at the change of a system. And if I just draw a box and say this is my system, I have no numbers. I have nothing with units, I have no information or data about that system to analyse. So the next step in our definitions is the definition of properties. And these are not mysteries, these are things you've been working with all the way through physics, chemistry, engineering, maths. But we're going to characterise them in a way that works for us. There's a couple of different forms, so I could tell you about the mass of something, or I could tell you about the mass of something per unit volume. I use that information in different ways. Both of them give me information about mass. One of them is a bit more generic, one of them is a bit more specific. So we'll have a look at these different classifications. A property is any characteristic of a system. So we've just spent some time working out what a system is. And on the way, I start waving my hands around the ideas of temperature, volume, pressure, mass. So these concepts are not strangers to us. These are the properties of the system. These are the things that we can watch change. We can measure them, we can understand them, and importantly, we can predict what happens. There are some extra little definitions So again, when I bold things, it's usually because they're code words. An intensive property is one that it exists independent of the amount of mass of a system. And I'll come back to this a couple of times. So temperature, pressure, and density. If I had a 10 kilo system or a 100 kilo system or a 1,000 kilo system, the density of that system, all other things being equal, the density is the same. The mass has changed, but the density, so this property of density has stayed the same. If I have this room, let's imagine that this bottle, I'm going to open the bottle so that now I can confirm that it's at the same pressure as the room. I close the cap. This room, or the air inside that bottle, very different mass of air, pressure is the same. So pressure is independent of mass, density independent of mass, temperature, bottle, room, very different masses, same temperature. Temperature is independent of mass. These are called intensive properties. Extensive properties are connected to the pressure. So the mass of connected to the mass. So the first one of those is the mass. Right? If I have twice the mass, I have twice the mass. And we keep track of what things would change if I had more or less mass. The other one that changes really quickly is volume, which is one of the reasons why we connect mass and volume, why we have the idea of density. And in thermo, we do a lot with the inverse of that guy, which is called specific volume, the volume per unit mass, as opposed to the inverse, which is density, the mass per unit volume. A lot of what we do, the reason we take the time to define intensive properties is that a lot of what we do, we try to keep independent of mass so that my answer for how does the system change as I do something can be scaled from this big to hundreds of megawatts or gigawatts of power. The analysis is the same if I can ignore the mass. So a lot of what we do is per unit mass. When we're doing the chemistry-related stuff, advanced thermo, you're doing combustion, and it's all about chemistry, you do it per unit mole. So the intensive properties where we normalize them by the mass or the mole, we do that to save ourselves time and give ourselves an efficiency in the calculation. So, we do a lot early on with boiling water. There's a reason why we do a lot with boiling water. What's a nice property of boiling water? How hot is atmospheric pressure boiling water? Yep, 100 degrees. And if it's atmospheric pressure in the room and I'm boiling water and I keep boiling the water up until the water's gone, it's going to have stayed at 1 atmosphere pressure. The pressure that's acting on that water is the pressure of the room. It's going to have stayed at 1 atmosphere all the way through that process. It's a nice thermodynamic process for us to analyse because it has some simplifications in it that let the maths be easy. If I have 2 kilograms of water boiling or 1 kilogram of water boiling at the same pressure, there's 2 different masses of water. I'm going to need a different amount of heat to boil them, but the temperatures of them through that boiling are the same. Those 2 systems, one was 2 kilos of water, the other was 1 kilo of water, we say that they are at the same state. So there's another code word. The state of the system is a shorthand way of saying all the properties. So if I say the system has the same state as this other system, or the state has changed, I'm saying the properties have changed. There's some of the properties we use all the time, temperature, pressure, volume, mass. Some of them, in this course, we won't use very much at all, but they're still valid. Thermal conductivity, viscosity, all these things. If I say the state of 2 systems is the same, all properties of that system are the same. This gets useful because if I can find a way to know the state, if I can find an easy way to know the state of the system, that means I could look up the properties from anywhere where this property information is recorded. And this is super powerful. It means I don't need to measure viscosity. If I can say that I know the state of the water because of some reason, and there's a very important category that we use for those reasons. If I can tell you that I know the state, I can tell you, therefore, that shorthand for not only do I know a few properties, I know all the properties of that substance. So I don't need to measure them. So how can I define for you the state? Let's just finish that off. As I said, it takes a different amount of energy to boil more water than less water. So when we're dealing with energy and power, we will be interested in the extensive properties. When we're doing the analyses, we'll now analyse it on a per kilogram basis and then say, okay, and how many kilograms were there? So we go energy per unit mass for a change. Now there was 2 kilograms, so let's double it. Okay, so that's equations of state. Now that we're interested in hunting down how do I establish that I know the state, we'll play with a couple of ideas. The answer to how much information I need to know depends on how those properties are connected. I've got up there a spring, and then a spring with a mass, and then a spring with double the mass. And what's the relationship between mass and distance of a spring? Half xk. Mass and distance?
Yes. And property of the spring.
So I need to know the force, so the mass goes to force. Yep. And then x, distance, and then k. So what I've got there is a really simple relationship. If I know something about the substance, the spring, which is k, the spring constant, if I know the force, I know the distance. If I know the distance, I know the force. So there, I only actually need to know one property of the system to be able to define all the other properties, useful properties of the system. In working fluids, I might need to know more properties before I can pin it down. We will get in the habit. So this kilo of water that we were boiling before at atmospheric pressure, we know is 100 degrees. Now what was interesting is I said the water's boiling at atmospheric pressure. What's the temperature? You guys said 100 degrees. You didn't calculate it. You didn't look it up. It was in your head. That was because you memorized it, but and because it's a fairly well-known number. But the exercise of how many pieces of information do I need to give you before you could tell me that? If I told you that the pressure was, that we were up on the top of a mountain and the atmospheric pressure was much, much less, would the temperature be higher or smaller? Right. So you may not know the number off the top of your head, but you know it's going to be smaller. You know that somewhere in this world I could probably look it up. If you told me the pressure, I could probably work out what that boiling temperature was. Somewhere there's a textbook or Google or whatever, I could probably work it out. Which means that I've only really given you 2 pieces of information. One was that it is boiling, and the other was the atmospheric pressure. We will do that over and over and over again. If I get 2 properties for working fluids, I've defined the state. They have to be independent properties, though. This example here, well, that's different words for effectively what I've just said. Okay. The key there is dependent and independent. Early on, as you write down, imagine you're beginning to solve a problem. System boundary, what's my working fluid? Now next step, how many properties do I know and have I defined its state? Once I've defined its state, I can continue. So early on, we will be looking for how many independent properties do I know and do I have enough to then say, we're done. The answer is I need 2 independent properties for working fluids, because I'm interested generally in pressure, volume, temperature, mass, all these things. So if I have 2 things that are independent and known, I can do this. An example of things that are not independent, density and volume are not independent. If I change one, if I change one, I do change the other. So we're looking for ones where if I change one, I don't automatically, by definition, change the other, unless I know what else has happened. Volume and pressure are independent because the other way to look at it is just knowing one doesn't give me the other. So the state postulate says two independent intensive properties. And let's keep going. So the Hooke's law, which was the spring law, was the F equals Kx. That's in the world of thermo, that's referred to as a equation of state. The equation of state says if you give me some of the properties, I can calculate the other properties. So it's not even that I'm looking them up. Depending on the system, there are actually already loads of equations of state that you know. We just haven't called them equations of state. If you're in Foundations of Electrical Networks or anything electrical, you would know that there is a relationship between voltage and current and resistance. I hope. I really hope. That is an equation of state for that system, for that type of analysis. And if I know two of the things, I can get the third one. The one we use all the time is what's called the ideal gas law. And I will tell you when we are ideal gas and when we are not. We'll do that on Friday. PV equals MRT is your ideal gas law. You may have seen it already. It's likely you've seen it already, either from high school physics or university physics. A couple of things in here. We've got pressure, volume, mass, gas constant, and temperature. So the gas constant, once I tell you that we're dealing with air or nitrogen or ammonia or whatever, I've defined the gas constant. There's another version of this where I use a universal gas constant, so I don't even need to tell you what it was, but I still need, actually, I do need to know what it was because I need the molecular weight. If I stuck a thermometer in the air, I could tell you the temperature, and if I defined my system, I could tell you the volume. At that point, I could tell you the pressure. I haven't measured the pressure, but if I knew the temperature, if I knew that it was air and I knew the temperature and volume of the room, I could tell you the pressure. And the mass, sorry, and the mass of the air. Sometimes the way these values connect is way trickier than just a simple equation. And the main time that happens is with water, or water at the conditions that we use it. So we will be interested in understanding when am I able to use neat, easy equations of state, and when is it hard. When it's hard, all the homework's already been done for you because someone has written it all down. Someone has written page after page after page of how the properties change with other properties. And they're called property tables, and we're also going to dig into those. So, this tool that's up there, at this point, you can do thermodynamic analysis. We'll give you an example. This room, system boundary, I close the door, no mass can change, so it has a mass, it has a pressure, it has a volume. I double the temperature in the room, what happens to the pressure? Times T by 2, what happens to P? Also, imagine it got hotter in here and I can't let any mass go through. Am I expecting the air to get more pressure or less pressure? The other way to think about it, we'll do that problem the other way around. I squeeze the pressure in this room by double. What happens to my temperature? Doubles. That's the thermodynamic analysis of the change of the properties and state of a system. By knowing the equation of state, and by knowing two of the properties, if I then tell you that something changed, and I tell you how it changed, you can then predict the final state. We didn't need to do that experiment to determine what the temperature was. Someone has done the homework already. If I change the volume, without changing the pressure, I could tell you what happened to the temperature. If I change the mass, I could tell you what happened to the system. There's lots of stuff in there that I can already do. That tool we use all the time. So this is one that I want in your head because it'll be one of your major tools off the shelf for thinking about something's changed in my system, can I work out what happened? The way to use it is to say what stayed constant, what changed, by how much, therefore what's the result? inside everything I've just said just then is this idea of change. We define that as the process. The whole point of the analysis is to understand what happened next, what happened after. What happened after some time passed, what happened after I squeezed things, what happened after I added some heat and it all got hotter. What was the change? Thermodynamics, what was the change in the energy? And so we've got systems, we've got properties, and now I need to know how do those properties change. They change through the action of some kind of process. Which process lets us work out the answer? Which is to say, saying what the process is gives me the maths to solve the problem. If I say this thing changed at a constant pressure with a constant volume, I have enough information, but I've given you information about how the process occurred. If I say the process happened slowly or quickly, if I say the process happened with heat transfer or without heat transfer, if I say the process happened with mass change or without mass change, I'm telling you something. And so we can trace the start and the end. We can put them down. The dots on the graph are the states. The state at the beginning, the state at the end. The line between them is the process path. Sometimes we don't care, sometimes we do. We're going to spend a bit of time over the next few weeks working out when we care and when we don't. Whether that was a straight line, a corner, a nice little arc. Sometimes I need to know, sometimes I don't. Sometimes I just want to know what was the end condition. Other times I need to know how much energy was used to get there, or how much energy would I need to put in to get there. And it depends on the process. So we will get a whole series of definitions for different process types. There's one last little step. Many of the processes we need to put in a little mathematical caveat, a little mathematical asterisk that says we need these processes to be occurring in what's called quasi-equilibrium manner. Literally the first few slides of the next lecture I will give a proper definition for quasi-equilibrium. The answer is, at this stage of thermodynamics, everything is fine. Everything obeys enough rules that we can do it. This idea of quasi-equilibrium, is it happening fast? Is it happening slow enough that the state, at any moment in time, the state of all the molecules is the same in my system? Everything we're going to analyse, the answer is yes. I flag it now because it means that there is a world, there is a set of processes where things happen so fast, explosions, detonations, stuff goes on, where you need different thermo rules. So we're just doing the intro thermo rules, so we're going to stick to the assumptions that make our life easy for now. But I want you to be aware that assumptions were made, so that one day when they're broken, you go, oh, hang on, no, I knew that. I knew that that was a thing. So that's us for what we've done over the last sort of 40, 45 minutes is lay the framework and the ground rules. To solve a thermo problem, we need a system with system boundaries, and we need to know how they behave. We need a state and properties, and then we need to know something about how they changed, because just watching something not changing is mathematically and engineeringly uninteresting. End result was state 2, the different state. So I'm going to need to know a few properties I'm going to need at least 2 properties at the second state to say I'm finished. And I've worked out everything that happened. After this, Friday, so 3:15, same room, we'll look at thermodynamic equilibrium, we'll look at the ideal gas, and we'll look at the ideal gas rule, and we'll play with it, and we'll look at processes and cycles. That's the bit where I'm going to actually give the maths or give the definition of each of these magical processes that we're going to use as tools. And the ideal gas law we'll play with a bit more. But that's us for today. Thanks.